So this is QuickDraw, an application made by Google, and if you haven't seen it or heard about it, it's an application where a human gets to draw an object and a neural network tries to recognize what the object is. So now this app has actually been around for quite some time, and as a lot of people used it, Google collected all of this data and they recently open sourced it to give us this, the QuickDraw dataset. So this dataset is a collection of over 50 million drawings across 345 categories. And using this dataset, we can make an application which looks something like this. This is my own rendition of Google's Quick Draw application, but just for fruits, right? So you can select what kind of neural network you want, either a convolutional neural network or a normal multi-layered perceptron, and you can draw a fruit. So I'm going to draw an apple now, and let's see if my application can detect what it is. So yeah, as we can see, there's a 99% chance that this is an apple. So that's pretty cool. Let's try drawing something else. Let's try drawing a banana. Yeah, so yeah, to make our own neural network which can classify drawings, we're gonna need the data set. So we will grab the data set from over here under the pre-processed dataset section. So we're going to grab the NumPy bitmaps. So what these bitmaps are is that they are a simplified form of the dataset, and they've been simplified into a 28 cross 28 grayscale size. So it is kind of like the MNIST dataset, but for a lot of different objects. So we can grab that dataset from over here, and this will open up a link where we can see a lot of different objects, from aircraft carriers to angels to whatnot, right? So you can do this for basically any object categorized here, but let's just do it for fruits. So let's search for apple, and I have the apple .mpy file here. So to code and train a neural network, we will be using Google Colab. So what Google Colab is that it is a completely online Python interpreter, kind of like your Jupyter notebooks. But the best part is that since the entire compiler is online, we have to have nothing installed on our system. And all of this is just a website link away. Also, Google Colab by default, the Python interpreter at Google Colab already has all of the major Python modules like NumPy, SciPy, TensorFlow, or Keras already installed. So we will not be facing any installation issues whatsoever. Another plus point about this Google Collaboratory is that it offers a runtime environment. So we can change the runtime type from a CPU to a GPU. Yes, they give free GPU service, and using GPU to train our models would make it at least twice or thrice as fast when compared to CPU. So that's great. And if by any chance there is a Python library which is or not already installed on Google Colab, we can always go ahead and install it via pip install. So I can just do pip install lxml or any Python library in fact, and run it over here, and that should go ahead and install it for me. The only change being that we are supplying a distinguisher at the beginning of this command, an exclamatory mark. So this is for Google Colab to know that whatever follows this exclamatory mark is not a Python syntax, it's actually a shell command. So I can execute any shell command like this by giving an exclamatory mark. So I can make a directory called test, and that should make a test directory for me inside my environment. So I can just say ls, and we can see data lab and the test directory is created. So that is Google Collaboratory, and we will be using this to code and train our entire neural network. So here I have the entire IPython notebook, or the entire code for making our own classifier. So first up, we're going to be making a new directory called data, so that we have a place to store our data sets. So let's execute that, and then let's enter into the directory. So we'll cd into that directory, and after that we are going to be downloading, at least for our purpose, we're going to be downloading the apple, pineapple, grapes, and banana npy files from this page over here. So we can get the link from here, And then we're gonna just use the wget tool for downloading the data sets. So one good thing is that since this entire thing is located on the Google servers, the internet speed is really fast. So I'm able to download a almost say 100 MB or 500 MB data set in like 2 seconds. So that's pretty cool. So now that the data set is done downloading, we can see if it's actually there. So I'm going to use ls. So we can see that apple, pineapple, banana, and grapes are over there. So we're going to go back into the root directory. So cd into that. And now we're going to make some generic imports. So let's run this. So we're going to be using scikit-learn, a bit of scikit-learn, and most importantly, we're going to be using keras. So keras is a very high level deep learning API built on top of TensorFlow. So we're going to import that as well. And then let's get to the code, right? So first we'll define some constants. So the number of fruits which I have here is 4, and the fruits which I have is apple, a banana, grape, and pineapple. So I'm just making a quick dictionary and having them key indexed because we might need this sort of an architecture later on. So by default, each of these NPY files, so let's take the banana NPY file, right? So this banana NPY file has around, actually it has a lot, thousands and thousands of different images of, hand-drawn images of bananas, right? But we do not need that many. So we're gonna be setting a number, right? So the number of samples to take in each class, let's define it to be around 5,000. So I'm only going to be using 5,000 samples per class. So 4 times 5,000, that'd be 20,000. So I'm going to be training my neural network on 20,000 images of fruits. And let's also define some other constants. So n epochs, or the number of epochs to train for. So I'm going to be training for 10 epochs. And then we have a files list. So in this list we define what are the name of the files which we need for training. So apple.npy, banana.npy, grapes.npy, and pineapple.npy. These should be in the same order as defined in this dictionary over here. So after that is done, I'm going to be defining a bunch of functions, mostly helper functions, which we're going to be using to help build our neural network. So I'm going to be explaining them as the time comes. So I'm going to execute that. After that is done, let's try to visualize the data set. So first, we'll just load, we'll use the load function which we have defined to load the data set. So the first argument here is the directory where the data is present. So in our case, is the NPY files are present inside the data directory. So I've specified that. The second argument is false uh, because of the fact that the NPY files which we download are actually flattened images. So they are technically 28 by 28 grayscale images, but they have been flattened out. So instead of being a two-dimensional array of 28 by 28, it is actually a one-dimensional array containing 784 elements, because you're flattening out each row and placing them adjacent to each other. So that's that. So this is false because we do not need to reshape our data. So we want our data currently, at least, to be in a one-dimensional form. And then here is a list of files which we need to be loading. So I just want the apple.npy file for now. So let's execute that. And then after that is done, we can visualize the first fruit. So yeah, that is the image of the first fruit which is available inside the dataset. So that's an apple probably. Now we can actually get started with the actual coding. So first, let's load the entire dataset this time. So I'm gonna load the all of the files which I have, that is apple, banana, pineapple, and grapes. And this time the second argument I'm passing it as true because I do want to reshape it to a 28 cross 28 form. That's because a convolutional neural network expects the data to be in a 2D format. But if you want to use a normal feed-forward neural network, a normal multi-layered perceptron network, then you do not have to reshape the data, and then you can just pass false over here. So after that, we will set a limit to all of the fruits. So what this basically does is that, remember we first set a limit. So we set the n value to be 5,000. So we only want 5,000 samples per case. So since there are more samples in each class, in each of the NBY files, we will set a limit such that we only take the first 5,000. So now fruits will only contain the first 5,000 elements from each class. After that, we will normalize the values. So each of the grayscale images present in fruits has a pixel value ranging from 0 to 255, right? Because they're grayscale images. But neural networks tend to perform a lot better when the values are normalized in a range from -1 to 1. So this is a normalized function which we've written inside our helper functions. So we're gonna be normalizing each of the fruits. So we're gonna be converting the pixel values which range from 0 to 255. We're gonna convert those values from a range from -1 to 1. So after that, we will make the corresponding labels. So this make labels function basically takes the number of fruits we have and assigns a label. So 0 stands for apple, 1 that comes from over here. So 0 label is for apple, 1 label is for banana, 2 label is for grape, and 3 label is for pineapple. Uh, so we know the label numbers, but we have to extend that to n. So what this basically does is that the first 5,000 would be 0, the next 5,000 would be 1, the next 5,000 would be 2, and the last set of 5,000 fruits would be a 3, because that's the order in which we are loading the data set. So that is the function make labels. After that, we will prepare the data. So we're going to split the entire data set into two parts, one part for testing and one part for training. So we have a X train, which has the features or the images which we need for training, and we have X test, which are the features or images for testing, and we have Y train. So Y train is the corresponding labels to X train, and Y test is the corresponding labels to X test. So we're going to be splitting the data set in a 5% size. So 5% of the data set would be reserved for testing purposes only. After that, we will be doing a one hot encoding on our dataset. So what one hot encoding does is that it takes the standard list of labels which we have, and it makes another format of a list, but this time it is a list of lists as shown in the figure. So each index of the one hot encoded list is corresponding to a class. So in this case, the first element would be an apple, the second element would be a banana, the third would be a grape, and the fourth would be a pineapple. And whatever the label is, there would be a 1 in that index and there would be a 0 in the other indexes. So now that we finally prepared our data for training, we can go ahead and design our architecture of the neural network. So in this block of cell, I've defined a convolutional neural network, and in this block of cell, I've defined a normal multi-layered perceptron neural network. Usually, when it comes to image data sets like the one we have right now, convolutional neural networks tend to perform much better. But since this is a relatively simple data set, even a MLP neural network like the one I've defined here does decently well. So for now, I'm going to be using a normal convolutional neural network. So what happens in this is that the first few layers of this network are convolutional layers. So what a convolutional layer does is that it takes the input image and applies a filter on top of it. After a filter has been applied, the image tends to become more simplified, and the computer or the program or the neural network in this case, can extract more features from the image. So first we apply two convolutional layers, and we just define the input shape in the first layer to be 28 by 28, since our images are 28 by 28, and the one here stands for the depth of the image. So since we are only using grayscale images, there's only one channel uh, to our image, right? If it was a RGB image, a color image, then the channel would be three, because there are three color channels, R, G, and B. Then we have a couple of max pooling layers. So max pooling layers is basically something like a resizing kind of layer. So what happens is that the max pooling layer takes in a 28 cross 28 simplified filtered down image, and it reduces or resizes the image to a smaller size so that it's easier to process. And then dropout is a tactic or a strategy where we randomly ignore certain weights or certain features of the image to get to make sure that we are not overfitting our neural network with the dataset. So it's a good strategy to have a dropout layer. And then after that is done, we flatten the image, and then we have a normal dense or fully connected neural network here. And at the end we have uh, we want the number of nodes at the end of the neural network to be the same as number of fruits. So now we know, so whichever node or whichever neuron at the end of the neural network is activated, we would know what fruit the input was. So that's the architecture of a convolutional neural network. Coming to a feed-forward multi-layered perceptron neural network, it's pretty much a fully connected neural network with a couple of layers. So the first layer has 600 neurons, with the input dimension being 784, because this time we are passing in a one-dimensional array, a flattened image array. And then again we have a dropout layer, and then we have another dense layer, and then another dropout layer, and another dense layer, and then another dropout layer. So as you can see, as the neural network progresses, the number of neurons in the network tends to decrease, and at the end of it we would have the same number of neurons as the number of fruits, again because of the fact that it's easier for us to know which fruit was the input depending on which neuron was fired at the very end. After that, it's we are pretty much completed with our architecture. So now we can compile our model, and we're going to use the Atom optimizer. These are some standard parameters. We can just plug them in directly and not worry about them that much. And after that, we will be training our neural network on the X-train data. So these are the training features. We would supply the training features and tell our neural network that these features correspond to these labels. That's stored in Y-train. And then we will say batch size equals 32, which means that we're telling the neural network to process only 32 images at one time. And then we're going to train it for the number of epochs which we've defined. So after that, we are pretty much completed with the training, and then we can evaluate our model. So since we had some features left at the side for testing purposes, we can supply them right now in the model.predict function. So we can give the testing features and ask our trained model to predict what the fruits are. So that would be stored inside a list called preds. And then after that, we can do a very simple check with the original Y test. So Y test has the actual labels which correspond to X test, right? So we can compare each element of preds and Y test, and if they are same, that means our model has correctly predicted the fruit, and so we can increment a score. And at the end, we can just make a quick fraction and print the accuracy, and then we can save the model with the extension .h5. So I'm going to call it fruits.h5, and then I can store or save the model. So let's run all of these cells and train our neural network. So I'm going to run this cell, and I'm going to run this cell. So I'm going to make a convolutional neural network right now, and then after that is done, I can train it. So the training step is the most time consuming part of the neural network, of this entire project. And since we have GPU support in Google Colab, it actually is pretty fast. So as you can see, each epoch takes around 9 seconds to execute, and we're training our neural network for 10 epochs. So that shouldn't take a long time. Done on your local system on a CPU, maybe it would take at least twice or thrice the same amount. So that's one advantage of training your models on the cloud, where we get free GPU support in this case at least. So I'm going to wait for this neural network to complete execution or to finish training. So almost done with the neural network's training. So while this is happening, I'm going to talk about certain parameters called loss. So loss is something which you want to minimize at every stage or every epoch. A good loss value would be something less than zero point 0.1. So since we have a value of 0.03, we're actually good to go. And you can see the accuracy over here of the neural network. It is currently 98.3%. So that's very good. So after that's done, we can see the final accuracy value after comparing with the testing features. So we got 95.7% of the testing fruits which we had. So our neural network was able to guess 95% of them correctly. So that's pretty cool. So now that the model is saved, we can download this model off of Google Collaboratory and then use them for our own application, right? So I'm going to have a link in the description on how to download files off of Google Colab. So after you've downloaded your file, you can make whatever application you want and make it. You can design it however you want to. So the entire code base would be available on my GitHub, and I've provided the link to that in the description. So yeah, thank you for watching.